Now that you have learned about the nomenclature of compounds, you have learned about Lewis structures of compounds. Now we're going to get into the shapes of molecules, and shapes meaning 3D structures of molecules. So why is it important to know the shapes of molecules? Well, all molecules have some sort of a 3D orientation, even the diatomic ones, because atoms have a volume. So for example, a hydrogen atom is very small. So H2, which is diatomic, is going to be very small. On the other hand, I2, which is also diatomic, is humongous. It's a huge atom, and so it's going to show different properties from hydrogen because of its size. Okay, and so it's not exactly a 3D shape, but it is still a 3D interaction. Okay, so we have to understand not only that you can have the shape of the molecule, but also the size sometimes. Okay, it's going to make a difference. When you start getting into larger molecules like triatomic and polyatomic molecules and ions, then the shapes become really important, okay? Because then you can have various different kind of shapes according to the number of electrons that any molecule has. So it becomes important. And why is it important? Because you can predict properties of molecules, all right, by the shape of a molecule. So for example, here is one, okay? Why is water liquid but carbon dioxide is a gas, okay, at room temperature? So right now, both of them look like triatomic molecules. H2O has 2 hydrogens and 1 oxygen, and carbon dioxide has 1 carbon, 2 oxygen. So both of them are 3 atomic structures. So if they're both triatomic, then what is so different about them? That one is a liquid which boils at 100 degrees centigrade, whereas carbon dioxide is a gas at room temperature. So physical properties can be determined by the shape of molecules. Then the other thing that is very important is molecular interactions, okay, that can be predicted by shape of molecules. So not only just within the water and within the carbon dioxide, but then how will carbon dioxide and water interact with each other? So for those, you really need to understand the shapes of both molecules so you can predict what the interaction would be. And the biggest part of this, or I should say one of the bigger aspect of this, is a number of biological functions occur because of molecular interactions. The classic example is, of course, hemoglobin. This is something that everybody will understand, but otherwise, a lot of the drug interactions that we talk about, those are all based on 3D structures. If you don't have the proper 3D orientation of a molecule, then the interaction will not take place, which means the reaction will not take place. Okay, and so this becomes really important in case of pharmacy when we are trying to synthesize proper medication for certain diseases. I'm going to go ahead and look at hemoglobin and explain that to you a little bit so that you can understand the importance of why the shape of a molecule is so important. So hemoglobin is a very important molecule in our body because it is what provides us oxygen. So it carries oxygen in our body. Once you breathe in the oxygen, it is hemoglobin is the one that is responsible for carrying it through. So what exactly is hemoglobin? It is 4 protein subunits. And here you can see in the diagram, these are the 4 different colors of the subunit. Each of these subunit is made up of a protein chain. So these are a lot of amino acids that are joined together to give this long chain. And then there are 4 macromolecules in here. The macromolecule is right here, which is called porphyrin. And porphyrin is the one that actually gives it the red color. The protein themselves are not colored at all, but the heme, okay, that's the hemoglobin part. The globin is the protein. The heme is the porphyrin part that gives it the red color. And this is what gives the red color to the hemoglobin. And here in the middle, it has iron. Okay, and so for example, people who have anemia will have iron deficiency. Okay, and this is also important in carrying oxygen from place to place. Here is the heme that is kind of settled into the units. So the 4 subunits make up hemoglobin. Each of those subunits has a heme, and then each of those heme, of course, has the iron. This figure on the right hand side shows you how the heme is actually interacting and binding with oxygen. Okay, so the subunit is so big, but these 4 amino acids, these are the ones that are responsible for the transportation of oxygen and then removing carbon dioxide from your body. Okay, so the heme not only interacts with oxygen, but also with carbon dioxide. So these are the 4 amino acids that are responsible, which means that the protein has to be in such an orientation that can actually hold the heme in this particular orientation to interact with oxygen. If the orientation is not correct, it will not interact with oxygen or carbon dioxide for that matter. So here is an importance of what we call the 3D shape of a molecule. And the molecule here is actually a huge one. Okay, so let's go on to the next part, which explains a little bit about why this is important. And this is important in case of sickle cell anemia, which is a genetic disorder, and it is an inability of the hemoglobin to carry oxygen. It does not bind to oxygen. The sickle cell actually looks like this. Okay, it's not even formed properly as a disc. So it looks like this. And the only difference between hemoglobin as in a normal cell versus a sickle cell is one amino acid. So glutamic acid is replaced by valine amino acid, and that takes the normal hemoglobin structure, which looks like this, to the sickle cell hemoglobin, which looks like this. And now this is unable to hold the hemoglobin, the heme in there. And once the heme is not being held properly, it cannot interact with oxygen properly. And so this is the whole importance here. And this is a very simple example of what happens in our daily lives with oxygen transport. But now you can imagine how challenging it is for us to make drugs and all that, so that we can make proper binding with all these proteins. So that's the kind of importance that we are talking about with molecule-molecule interaction as far as the 3D structures is concerned. So let's really get into the molecular geometry. It is a three-dimensional shape, as we just said. And as soon as you get into a triatomic structure, then you really get into geometries, because with 3 atoms, now you can get angles. Okay, and so we talk a lot more about triatomic and above molecules. We don't talk so much about diatomic here. Geometry can be predicted by Lewis structure, so you really should master the Lewis structure before you attempt molecular geometry. And then, which is something called the VSEPR theory, which is a valence shell electron pair repulsion theory. Yeah, it's a little bit big. You can call it VSEPR if you want to, or you can call it VSEPR. I generally end up calling it VSEPR theory. So the VSEPR theory ends up telling us how to draw the molecular geometry, and it is based on the fact that if you have electrons in there, they will try to move far away from each other so they can minimize the repulsion. And in very basic terms, that means that negative is going to repel the negative, so they're going to try and get as far away from each other as possible. Okay, and so that is what the repulsion part here is. Okay, so electrons will repel each other. So what is it that you need to know in order to predict molecular geometry? Well, first of all, you need to know the Lewis structure. If you don't know the Lewis structure, then it's going to be very hard for us to predict the geometry of a molecule. The next thing that you need to know is the electron domain geometry. Electron domain geometry is just trying to figure out how many total number of electrons you have, because for VSEPR, you need to know the electron domains, okay, that we have, the total number of electron pairs. So that's why you need to know this. Once you know this, then you can go on to predict what the actual shape of the molecule will be like. In some cases, the electron domain geometry is the same as the molecular geometry, but in some cases it's not. And then if your Lewis structure is wrong, everything else is going to be wrong. So work on your Lewis structure to make sure that you have the right. So let's look at the different kinds. Okay, so we can have 2 electron pairs, 3 electron pairs, and 4 electron pairs. Okay, we have more also, we'll get there, but we'll start with 2, 3, and 4 electron pair. When we talk about VSEPR shapes, by the way, and we say there are 2 electron pairs, we are pretty much talking about the central atom, okay, just the central atom. We don't care what's on the terminal atom. Not that we don't care, we do care. But as far as the shape is concerned, it is the central atom that drives the shape. So when we say we have 2 electron pairs, it means that on the central atom, we have 2 electron pairs. You can have atoms that are terminal, and those terminal atoms can also have a lone pair of electrons and extra electrons hanging around, but those are not going to help us in determining the shape of the molecule. So the shape is determined only by the central atom. Okay, all right. So now let's get to it. So if we have two electron pairs, those two electron pairs are going to be farthest apart from each other on the opposite sides, because that's how far they can repel each other, 280 degrees. Okay, and if one of them tries to shift farther away, then the angle is going to get smaller on the other side. So the farthest they can get away from each other is 180 degrees, and that is called a linear arrangement, okay, or a linear shape, a linear electronic geometry, whatever you want to call it, but it's an arrangement, okay, and it's linear. When you have three electron pairs, again on the central atom, if you have three electron pairs, then the geometry is going to be trigonal planar. Planar meaning it is still flat molecule. In the case of linear, it's still flat. Okay, we haven't really gone into a 3D thing. So trigonal planar is also flat molecule. And now just imagine a triangle. Okay, and so the atom, the central atom is in the middle, and then you have these three lines coming out. What are these three lines? Okay, these three lines can be anything. They can be an electron pair, or they can be atoms. Okay, so you can draw them whichever way you want to. Okay, we haven't quite learned where you draw the atom or the electron pair. You can draw the electron pair here, on the top, on the right. It doesn't really matter. What is important is that you have three electron pairs. Those three electron pairs can be bonding or non-bonding. Okay, and so we have three electron pairs, and that gives a trigonal planar arrangement. Again, we're not getting into shape yet. Okay, we're just talking about electronic arrangement. If you have four electron pairs, then now the shape gets into a 3D shape. So now you can imagine a pyramid, and in the middle of the pyramid is your atom, and then here are the four electron pairs coming out. Now the bond angle between them is 109, and that's far away from each other as they can get. Okay, the bond angle in trigonal planar was 120. So in all of these cases, the atoms are trying to get away from each other as much as possible. Whether they're atoms or electron pairs, it doesn't matter. Okay, but they're trying to get away from each other as much as possible. With the tetrahedral, we're getting into a 3D shape, okay, because it's not planar anymore. Again, think of a pyramid. Then the other two shapes that we are still working on then are the 5 electron pairs and the 6 electron pairs. In case of the 5 electron pairs, this is what the structure would look like. Now this is a bipyramidal. Okay, so just imagine two pyramids stacked on top of each other opposite way. Okay, and so trigonal, bipyramidal, and again the black lines here indicate to you the 5 electron groups. Okay, and remember again, these 5 lines can be electron pairs or atoms. We don't know that yet. Okay, we're going to work on that a little bit later, but for now this is what it is. Now here the bond angles are a little bit different, because you have these two lines or two electron pairs that are going totally opposite each other, and so that is 180 degree. Then you have these three electron pairs that are in one plane, and this one plane is separated by 120 degrees, and then you have a plane of electrons going up and then one pair going over here, and those two pairs are separated by a 90-degree angle. And this is the best, okay, that happens when you have a 5 electron pair arrangement. Okay, this is the farthest they can get from each other. Again, these can be atoms or electrons. Okay, it doesn't matter. We have to still figure that out. In case of the 6 electron pairs, where you have 6 groups around the central atom, then this is what it would be like. Now our pyramid actually is 4 square. Previously in trigonal planar and trigonal bipyramidal, our pyramid was a triangle, okay, at the bottom. But now in case of the 6 electron pair, our pyramid is a square base, okay, so like the pyramids of Egypt, okay, so they're all square based. And then you have a pyramid going up, and then there's the reflection of the pyramid. Now you have 4 of these electron groups going in the same plane, and then 2 of them going in totally opposite direction. This shape is called octahedral, okay, or this arrangement is called octahedral, and you have two different bond angles here. One is the 90-degree bond angle, which is between the vertical and the horizontal one, that is 90 degree, and then there is the 180 degree going from top to bottom, okay, and then between this plane, okay, over here, the square plane, that is also 90 degrees. So you have two angles over here. In case of trigonal bipyramidal, there are actually three angles here. So now we have the arrangement for 2 electron groups, 3, 4, 5, and 6. Okay, so now we've covered pretty much all electron groups. Looking at all these shapes now together in one slide, right here on the top, it's shown to you what is called the balloon model. And technically speaking, if you tie the balloons together, they will try and be as far away from each other as possible. You can try that out if you want to. But in any case, this is a nice little demonstration of the shapes of the molecules. So we'll start with the 2 electron groups, go on to 3, 4, 5, and 6. Okay. When we say we have 2 electron groups, those 2 electron groups are groups. Okay, so whether they are single bonds or double bonds or triple bonds, it doesn't matter. Each of those number of bonds are grouped as one, okay, which means that you have 2 atoms coming out of the central atom. Remember, the central atom is the key, okay, not the terminal atom. But the fact that you have 2 terminal atoms over here, this is the structure of carbon dioxide. So C is in the middle, and then you have oxygen and oxygen. And these bonds here, these indicates that you actually have double bond. But those double bonds are counted together as one electron group, okay, each. So which means that carbon dioxide has 2 electron groups, and if it has 2 electron groups, then the shape is going to be linear. And this is what CO2 looks like. Here is for 3 electron groups, which is supposed to be trigonal planar, and that is SO3, okay, sulfur trioxide. Sulfur is in the middle with oxygens all on the 3 sides. Now, these bonds here, you can see that there is one straight bond and then one with a dot, dot, dot. The dot, dot actually indicates the resonance part here, okay, and so electrons are moving so fast that they're distributed all over. But it doesn't matter that they are. The fact is that there are 3 electron groups, 1, 2, and 3. So whether it's a single bond, a double bond, or what you would classify as a 1.5 bond if you wanted to. But in any case, there are 3 electron groups, and because there are 3 electron groups, this is the best orientation they can have, which is trigonal planar, and that's what it would look like, okay, if you were looking at a model. Now keep in mind that linear and trigonal planar, they're both planar, okay, which means they are kind of like two-dimensional, except they're not two-dimensional because obviously atoms have volumes, okay, but they're flat molecules, okay, as we can say. All right, now we get to the 4 electron groups. In case of 4 electron groups, the structure that's shown here for you is methane, CH4, carbon in the middle, and then 4 hydrogens. Okay, now we have 4 electron groups, 1, 2, 3, 4, and this is what the balloon shape is going to look like. One thing I would like to remind you of, that these balloon shapes that you see are the closest representation that you will see of any kind of a molecule, because bonds are really not shown as sticks, okay? We show them as sticks only because our mind is so limited, okay, in what we can visualize. But technically speaking, remember, atoms are all round, and if they're round like balls, then really you don't have the stick in there, okay? And so when you look at this representation here, this really is what the molecule would look like, okay, that you have these, that you have the carbon in the middle, a circular atom, and then the 4 hydrogens are going to be around it. There are no sticks, okay, that are holding this molecule together. Then we have the 5 electron group over here, which the molecule here is iodine pentafluoride, and here is iodine in the middle, and then we have the 5 fluorine atoms all around. Now remember, fluorine technically has electron pairs, and those electron pairs do not matter over here, as I said to you. Whatever the terminal atom is, it can have as many electrons as it wants. It's not going to determine the shape of the molecule. Iodine is going to determine the shape of the molecule. All right, so it has 5 electron groups, 1, 2, 3, 4, 5. So then the shape becomes trigonal bipyramidal. Okay, and the nice green balloons show that you have two atoms going up and down. Then we come to the 6 electron groups, and the 6 electron group here is sulfur hexafluoride. Again, sulfur in the middle, and now you have the 6 fluorines all around it, and this is the farthest away they can get from each other, and that's the octahedral shape, and that's what the balloon shape looks like. Okay, and so sulfur is in the middle here. So this is a nice little representation of what all of these groups look like. Now we're getting into something a little bit different than what we had before. Okay, in the previous slide, we dealt with electron pairs, which were all bonding to the central atom. Now, in this case, we're going to talk about electron pairs that are also the lone pair of electrons. Everything that we dealt with in the previous slides were where everything was bonded to an atom. Okay, so there was physically an atom present there. But what happens if you have electron pairs that are not bonded, okay, which are called the lone pair of electrons? And I mentioned that to you back in Lewis structures that this will become a little bit important later on, okay, and this is now where it is important. So here the electron pairs are divided into 3 columns where you have the total number of electron pairs, and then the next 2 columns tells you how many of them are bonding and then how many you have of lone pair. The next column here is the arrangement of that pair, which is also called the electron geometry, and the arrangement was that if you had 2 electron pairs, then the shape would be linear, and if you had 3 electron pairs, then the arrangement would be trigonal planar, and if you had 4 electron pairs, it would be tetrahedral. Okay, so that's what the electron geometry is about, and the electron geometry will not go wrong in the sense that if you have trigonal planar, then the bond angle should be 120 always. Okay, that's not going to change. When you have a tetrahedral, then your bond angle is always going to be 109. That's not going to change. Okay, that is the importance of the arrangement of pairs and the electron geometry. The next column here is the molecular shape then. Okay, so looking at what we had from the electron pairs and looking at the electron geometry, we can come up with the shape now. Okay, in this molecular shape column, there are 2 things here. One is the shape, and the next thing here that you see is called the AXE formula, AXE. And I'm a very strong believer of the X formula because it really helps me determine what the shape would be of a molecule. So it helps me determine the arrangement as well as the shape. All right, so which is why I strongly believe in it. And this is how you I understand the X formula. A is the central atom, X is the number of atoms that are attached to the central atom, and then E are the lone pair of electrons. So in case of the first case where you have 2 electron pairs, both of them are bonding, there are no lone pairs, so the formula will be AX2. No E required because there are no lone pair of electrons. Okay, so it's AX2. So as we go on, I will explain the formula to you as well. Then the next column here is the molecular geometry, which means what will the shape look like in 3D. And then there's an example here for you. Okay, so we'll go through it one by one. So the first one, the linear one, is usually very easy. So you have 2 electron pairs, 2 of them are bonding, or both of them are bonding, and then the electron pair arrangement would be the linear. The electron geometry, okay, is linear. The shape then will be linear. The AX formula is AX2, central atom 1, and then X is equal to 2, which is the 2 atoms that we have. So here is the central atom and then 2 atoms that are bound to the central atom. Okay, and so the molecular geometry is linear. Example is beryllium difluoride. Okay, and this is what it looks like. Going on to where you have 3 electron pairs. In the 3 electron pairs, now you have 2 possibilities. Okay, one possibility is that all 3 of them are bonded. Okay, bonded meaning there is an atom attached to it. The other case is where 2 of them are bonded and you have 1 electron pair that is left over. So that's here 1 lone pair of electron. So again, all 3 of them bonded, and then in one case 2 bonded, 1 electron pair. In either case, the arrangement is still trigonal planar because the total number of groups of electrons you have is 3. Okay, so the arrangement is still trigonal planar, but the shapes are going to be different. Okay, so let's look at the first one where you have only the bonding pair. Okay, which means you have AX3 is the central atom and 3 are X3 are the 3 atoms that are attached to the central atom. So this is what it is. Okay, this is what it looks like. And so this is a very traditional trigonal planar shape, okay, which is BF3 as we saw in the previous slide also. Things are a little bit different when you have 2 bonding and 1 electron pair left over, okay, 1 lone pair of electron left over. So now the molecular shape will be slightly different, okay, but let's talk about the AX formula first, all right. And so this is AX2E1. A is the central atom, which is the green one. X2 are the 2 atoms that are attached to it, and then E1 is the 1 lone pair of electron that is left over. And that E1 indicates that there is a lone pair of electron which is not bonded to anything. And what that really means is that you will still have the effect of the electrons, which means you will still have the repulsive effect of the electron. I didn't say it the right way, the repulsion, okay, or the force, okay, of the electron pair, but there is no atom there, okay, which means that this space is kind of empty, unlike the trigonal planar where there was an actual atom there. So you had the group of electron, but there was an atom. But in this case now, where you have a lone pair of electron, there is no atom. However, it is still exerting its repulsive force, okay, and so which means that these 2 atoms will still feel the force of these lone pair of electrons, which means that the geometry, okay, or the arrangement is still trigonal planar, okay. The electronic geometry is still trigonal planar, but because there is no 3rd atom there, the shape will be bent, okay, because now you can technically see only 3 atoms there, and so now this is a bent shape. Now, one of the other things that is really important over here to understand is that this bent shape is coming from trigonal planar, and because it's coming from trigonal planar, the angle here should be, yes, 120. Okay, so in this bent shape, which is coming from trigonal planar, should be 120 bond angle. Okay, so the example here is for SO2, sulfur dioxide. Here is the shape of the molecule. Here is the lone pair of electron, which is exerting the force. Here are the 2 oxygens. Hopefully things are becoming a little bit clearer, okay, with how this electron geometry is working. In case of 4 electron pairs, now you can have 4 electron pairs that are completely bonded. You can have 3 of them bonded, but 1 lone pair of electrons, and then you can have 2 bonded with 2 lone pair of electrons. In any of these cases, because you have 4 electron groups, the electron geometry is still tetrahedral, okay, which means that the bond angle is still 109, okay, so that is still valid. What is going to be different is, of course, the shape. So now we have 3 different shapes possible for all of these 3 different electron types that we have. So in the first case, where you have all 4 atoms that are bonded together to the central atom, it's a tetrahedral shape as we did before with methane, CH4, and the AX formula is AX4, okay, where the central atom is carbon, and then the 4 hydrogens represent the 4 here, okay, and so this is what the shape would look like, just like we did in the previous slide. So the change comes when you start having 1 electron pair, okay. So for example, when you look at ammonia, which is NH3, and this is the Lewis structure of ammonia, where you have the 3 hydrogens and 1 electron pair that is left over for nitrogen, that electron pair is still going to have an effect on the other 3 atoms, just like we had before in the trigonal planar. So now that effect is going to still have that repulsion effect, and so therefore these atoms will still be pushed down, and so the shape here will be now trigonal pyramidal. In the top case over here with the 3 electron groups, this was trigonal planar because it was a flat molecule. This molecule here with the AX3E1 formula, this is trigonal pyramidal because the pyramid shape is still retained. You don't have the 4th corner of the pyramid because there is no atom there, but the effect is there, okay. The AX3E1 indicates you have 1 central atom, 3 electron groups which are bonded to atoms, and then 1 lone pair of electrons, okay. The bond angle here should be, yes, 109, okay, because that is the bond angle of tetrahedral. Very good. Going on to 2 and 2 now, where we have 2 bonding and then 2 non-bonding. Again, because you have 4 electron groups, it's still tetrahedral. This is what it would look like. An example of this is water, where oxygen is in the middle and the hydrogens are on either side. But oxygen now has two lone pair of electrons. So if it has two lone pair of electrons, both of them are going to have an effect. Okay, and both of them are considered as individual electron groups, okay, as we did before. So these two electron groups are also having an effect, and the atom is not there, but still, okay, the repulsive force is there. So now the shape is going to be bent, okay. The X formula is AX2E2, A central atom, two atoms for X, and then two electron pairs, all right. And the shape is bent because these two electron groups don't have any atoms, okay, to show for. So this is what the molecule will actually look like. The bond angle here should be 109, okay, because this is coming from tetrahedral, which means that the two bent shapes that we have talked about so far, one bent coming from trigonal planar and one bent coming from tetrahedral, both of them will have different bond angles, okay, and that is what differentiates these two molecules is the bond angle. Otherwise they're both called bent, okay. So the shape is still bent, but remember the electron geometry is different, okay. One is trigonal planar, the other one is tetrahedral. This slide is a little bit busy, but I will tell you what's on it, okay, and it'll be easy to then figure out how to use this. This is just a table of all the different electron groups and the different shapes that are possible for molecules, okay, with those electron groups. So for example, if you have two electron groups, this is the only shape that is possible, which is linear. If you have three electron groups, there are two Ax formulas possible, which means that there are two shapes possible, trigonal, planar, and bent. And then here are the examples, okay, for these two different shapes. And of course, I urge you to go ahead and draw all these structures and then actually verify that these are the shapes possible. Okay, and then of course, here are the bond angles. Now, the bond angles for three electron groups are going to be the same because the electron geometry is trigonal planar. And the same thing goes for four electron groups, where these are the three Ax formulas possible. Again, since the electron geometry is tetrahedral, you will have only one type of bond angle, or the bond angle that goes with tetrahedral geometry. These are the three examples possible, and then these are the three shapes possible when you have a tetrahedral electron geometry. So that's how it goes for these five also electron groups and then six electron groups. These are the different possibilities. So take some time and go over this one by one. You don't have to memorize the entire chart. You do have to know 2, 3, and 4 definitely, okay? But 5 and 6, I would like you to understand it so you can make a reasonable judgment when you see the Ax formula, so you can come up with the right electron geometry at least, okay? And give me the proper bond angles. This one here does have the shapes. Okay, so you can use this one also if you want. This does not have the Ax formula, okay, in there. It has some other information. It has the bond angles in here. It has the 3D shapes of it, okay. So the previous slide did not have the shapes, but now you have the shape, all right. So again here with the two electron groups, here is the linear shape. And here with the 6 electron groups, here is the linear shape. Okay, this is what it looks like, which means the 4 electron groups are actually on the plane, okay, over here. And then again with number 5, okay, when you have the 5 electron groups, then these are your 2 atoms, and the 3 electron pairs then are on one plane. Okay, that's kind of what I was talking about before. But anyhow, you can go through this slide also. This shows you a little bit about the different shapes. So for example, with 5 electron groups, the maximum number of atoms possible is 5. So the shape is trigonal bipyramidal. If it is 4 atoms and 1 electron pair, the shape is seesaw, sawhorse, okay. Yeah, pretend that, you know, this is sitting on the ground, and then you can sit over here, your friend can sit over here. That's the sawhorse or the seesaw. And then this one here, when you have 3 atoms and 2 electron pairs, then you get the T shape, okay. And I know some of you may want to think that why are these 2 electron pairs not on the top and the bottom? But I will tell you not to worry about it right now. Just remember, this is what it would look like, okay. All right, and then here is the 2 atoms, okay, which are farthest apart from each other, so on and so forth, okay. Let me solve a problem with you. And this one is, of course, making a model. So use the VSEPR model to predict the geometry of the following molecules, ASF3 and PH4 plus. So one is a neutral molecule, the other one is a cation. So let's start with the first one, which is ASF3. The first thing we do is count how many total valence electrons it has. And so arsenic, which is in group 5, has 5 electrons, and we have only 1 of arsenic, so that's the one here. Fluorine, we have 3 of fluorine, and each fluorine has 7 electrons in the valence shell. So by the time you do the multiplication and add everything up, they're going to be a total of 26 valence electrons. And remember, you have to account for all the valence electrons in a Lewis structure. Arsenic is going to be the central atom. Why? Because arsenic is on the left hand side of the periodic table, or it has lower electronegativity than fluorine. You can use either of those principles. So right here is the Lewis structure for arsenic trifluoride, where arsenic is the central atom. Now if you were really doing this on your own, you would start with just drawing the 3 lines first. Okay, just making the one bond that gives you 6 electrons, and then of course you fill out all the valence electrons like we did in the previous chapter. So once you have the proper Lewis structure, then you will go ahead and try to figure out what kind of geometry it has. So the way you start by, the way you try to figure this out is by trying to do the axe method. I like the axe method a lot. It helps with so many different molecules. So the way you do this is you take a central atom, which the central atom in this case is arsenic. So the central atom is A in the axe model. And then you look at how many bonding groups there are. So in this case, there are 4 bonding groups, 1, 2, 3, and 4. Okay, so there are 4 bonding groups of electrons. And remember, a double bond counts as a 1 group. Triple bond counts as a 1 group as well. Okay, so this is 4 bonding groups, but the way the bonding groups are distributed is that you have 3 atoms, fluorine. So that's X, that is 3 of that. And then you have 1 lone pair, which is the E. Okay, so that's the X model. So AX3E. What the AX3E tells you is that you have the 4 bonding groups, and the 4 bonding tells you that your geometry is going to be tetrahedral. Now this gives you the electronic geometry. It does not give you the shape. Okay, you still have to figure out the shape. The electronic geometry helps you figure out what the bond angle is going to be from tetrahedral. So if you have a 4 electronic geometry, a tetrahedral electronic geometry, then the bond angle is going to be 109, okay, approximately. But in this case, we are asked to predict the geometry. So then from here, you go on to figure out what the geometry is going to be, the molecular shape, okay, is going to be, and that is going to be trigonal pyramidal, because if you take the AX3E, in which we have 4 electron groups and 1 lone pair of electron, then that comes out to be trigonal pyramidal. Let's look at another one here, PH4 plus, and again you do the total valence electrons, and so now you have phosphorus, which has 5 valence electrons, and hydrogen, which each hydrogen has only 1, and you have 4 of those. And then you also have to account for the plus. Plus means that you have subtracted 1 electron. 1 electron has been removed. Where it is coming out from, of course, that is your Lewis structure. Okay, so we'll look at that also. But the total valence electrons are, of course, then 8. And phosphorus here is going to be the central atom. Why not hydrogen? Because hydrogen is always terminal. It's never going to be central atom. Its valency is always 1. Okay, so hydrogen is a little bit of an exception in a lot of cases. So right here is the Lewis structure for PH4 plus. Phosphorus in the central atom, and here are the 4 bonds, okay, which means that phosphorus is sharing all the 4 electrons with the hydrogen, and these are all the 8 electrons all accounted for. Okay, so there is no lone pair left anywhere, no extra electrons, okay, because you actually got rid of 1, so you put everything in square brackets and put the charge outside. Okay, that shows you that you have the right Lewis structure for this. So without showing you the answer over here, you can look at this and say, yeah, this one seems to have 4 electron groups, 1, 2, 3, 4. The ax geometry for this one should be AX4. Okay, no E because there are no lone pair lefts in here. Okay, so it's AX4. AX4 tells you that you have a tetrahedral geometry, and in this case, because you have AX4, you have 4 atoms as well. That means your shape is also going to be tetrahedral. Okay, in this case, so AX4 electronic geometry is tetrahedral, and molecular geometry is also tetrahedral. Molecular geometry is also what we call the shape. Okay, so that's how this one works. Another solved problem, use again the VSEPR model to predict the geometry of the following molecules. So ICl3 and ICl4 minus. Okay, both of these are iodine compounds, or you can say also within the halogen groups. One again is a neutral and one is charged compound or an ion. So let's look at the first one, which is ICl3, iodine trichloride. And both of the iodine and chlorine, they both have 7 electrons in the valence shell. By the time you add everything up, you have 28 valence electrons. Iodine is going to be in the central. Why is it going to be central? Because it has lower electronegativity. So when you're looking from left to right, the left is in the middle. When you're looking top to bottom, the bottom one is in the middle. Here is the Lewis structure for it. Iodine here is in the middle, right here. I know it kind of looks like is it a line or is it an I? It is an I. Okay, so it's right there. And then you have these 3 bonds, okay, with chlorine, and then you fill in all the valence electrons. Okay, there is no electron removed or added. So you just place in all the electrons to give the valency. Okay, so each chlorine is going to have 6 electrons because one is bonded, and then for iodine you have bonded 3 electrons, so then 4 electrons are left over. Okay, for this one. So let's do the AX model for this one. You have the central atom, which is iodine, which is A, and then you have the 3 atoms, so which means AX3, and then you have 2 lone pairs over here, so AX3E2. Okay, so that is going to be the bondings, okay, or the bonding region or the bonding pairs. So AX3E2. So the electronic geometry then for this, okay, because this is 5 bonding pairs now, or 5 groups, okay, that you have, is going to be trigonal bipyramidal. Now remember, by the time you get to 5 out of 4, you're talking about an expanded valence shell. Okay, so this is not the stable octet thing. This is an exception to the octet rule. So by having 5 electron pairs, you're talking about 10 electrons, and so that is expanded valence shell. But in any case, this is trigonal bipyramidal structure. But it can't be a bipyramidal because it doesn't have the 5 atoms. It has 2 lone pair of electrons, so it's only AX3 with 2 lone pairs over here, and so the geometry is T-shape, exactly the way it's drawn. Now, if you had drawn the Cl coming like this as a, like a fan, that's fine too. By the time you draw the proper structure and write out the bonding geometry, you will know, okay, that it's going to be a T-shape structure. Let's look at ICl4 minus, and in this case, again, go ahead and add up all the electrons that you have. Again, iodine and chlorine both have the 7 electrons in the valence shell. Now it is minus, so you're going to go ahead and add 1 electron to this. So it becomes a total of 36 valence electrons, and again, iodine is going to be the central atom because of low electronegativity. So here we are with the structure. Iodine again is in the middle, and now we have 4 chlorines over here. Now the 4 chlorines, they're all single bonded, so they all get the 6 electrons they're supposed to get for their valence electrons because one is being shared. And iodine now remember over here it had 4 electrons, okay, in the center it had the 4 electrons, but if you don't add the charge, the 4th electron technically has bonded with the chlorine, but because you have another electron here, iodine still has the 2 electron pairs, okay, in here. So again, you put the square brackets and you put the negative here. So because of that extra electron, that electron went to iodine over here, giving again iodine 2 electron pairs. So the Ax formula for this, AX4E2. Hopefully you can do this fast enough now. Okay, so now there are 6 bonding regions or 6 bonding groups. 1, 2, 3, 4, 5, 6. Okay, and then AX4E2, that's going to be the Ax formula for this. The electronic geometry becomes octahedral because that's for 6 electron groups, all right? But in this case, you only have 4 atoms. You don't have 8 atoms. So in this case, the 2 are just the lone pair of electrons. For something that is AX4E2, the geometry is square planar, or we can say that the shape of this molecule or ion is going to be square planar. Okay, so keep the chart handy that I drew out for you and use it as much as you want. For now, you may not have it in the exam, of course, but at least use it to answer these questions so you get comfortable with it. What if you have more than one central atom? Because we're not always working with small molecules. We can have larger molecules also, and actually there are large molecules. Okay, that's really most of the molecules. So for example, we have something like CH3OH. Okay, and in CH3OH, we can see that we have 2 central atoms. One of them is the carbon over here, and the other one is oxygen. Okay, remember hydrogen cannot be in the middle, so it is going to be terminal. Okay, and so this is what the molecule is, and this is what the structure looks like, okay, of the molecule. So you have carbon here with 3 hydrogens, and then oxygen with hydrogen over here and carbon over here. Remember, carbon has to have 4 bonds. So 1, 2, 3, 4. Oxygen has to have 2 bonds. So 1, 2. Carbon does not have any lone pair of electrons left over. Oxygen does. Okay, it has 2 electron pairs left over. When you do the shapes of molecules, when you have more than one central atom, you will actually have 2 shapes because you have 2 central atoms. So now you have to deal with each of them independently. All right, so let's deal with carbon first. And carbon geometry is AX4. So A, and then it has 4 atoms. It doesn't matter that our oxygen is bonded to something. We'll deal with the oxygen later, but right now, carbon is bonded to oxygen also. Okay, so it has 4 electron groups around it, and that's what AX4 is for. So there are no lone pairs that are left on carbon because everything is bonded, which means that the shape should be tetrahedral, okay, for carbon. Now let's look at oxygen. For oxygen, the formula is going to be AX2E2 because now you have oxygen which has 2 atoms in it and 2 electron pairs in it. Okay, so AX2E2, which means you still have 4 electron groups. Okay, so you still have the 4 electron groups, but now you have 2 lone pairs of electrons and only 2 atoms. And if you have 2 lone pair of electrons and only 2 atoms, then the shape is going to be bent. Okay, so which means that within the same molecule, you can have 2 shapes in here. Okay, and so this is what the molecule will look like, all right, where one is tetrahedral. The other one is also tetrahedral in its geometry, but in its shape, it is bent. Both bond angles should be, yes, 109. One of the last things to do in case of the shapes of molecules is what we call dipole moment, okay, and polarity of the molecule. So first of all, polarity is the degree of separation of charge, okay, in a molecule. We've done this before in the previous chapter when we talked about polar bonds. And when we had polar bonds, it was because one of the atoms was more electronegative than the other. And so if one is more electronegative than the other, it will pull electrons towards itself. And if it does pull towards itself, then it gets a partial negative charge. Okay, and that's what this delta negative is. And which means that the other atom will get the partial positive charge because now it has a little bit less electrons, whereas the more electronegative element will have a little bit more electrons. So the delta sign indicates a little bit. Okay, and the negative and the positive, of course, is the electron distribution. So this is bond polarity, okay? And if you remember, you drew out an arrow, okay, which was like this, with a little crosshair on it, and that showed to you where the more electronegative element was, okay? So that's what we've done before. Now we're going to follow up on that, okay, and see what is dipole moment, because that what we just learned was polarity of a bond. So dipole moment now is actually the measure of how much that molecule can move in an electrical field. So if there is any kind of a charge separation, then the molecule is going to move. Okay, but there are some other rules also. All right. And dipole moment, by the way, is not just for the shapes of molecules as in triatomic or polyatomic molecules and ions. It is also for diatomic molecules, because diatomic molecules can also have charge separation. So for example, HCl, that has a dipole moment because there is a charge separation going on. So some molecules will have dipole moment, whereas some molecules will not have a dipole moment. Any molecule that does not have a dipole moment are called nonpolar. Anything that has a dipole moment are called polar molecules. For us, that's all we are concerned about, is if a molecule is polar or not. Technically speaking, dipole moment is a number, okay, because it is a measure. So it is a number, but we're not worried about that, okay? We are worried about the fact whether something is polar or nonpolar. So how are you going to determine if something has a dipole moment or not, or whether a molecule is polar or not? These are the steps that you need to follow. And if you follow this diligently, you're not going to get it wrong. So first of all, draw the Lewis structure. If your Lewis structure is not wrong, nothing is going to be right. We talked about that before also with shapes, because the next step is to draw the shape of the molecule. So Lewis structure first, then you determine the shape of the molecule, then you determine the electronegativity of each of the atoms from the periodic table. You already know the trend, okay, which is that electronegativity increases as you go to the right and decreases as you go down, okay, a group. So that is the electronegativity that you look at the periodic table for. Then the next thing to see is if the molecule is symmetrical or not. If the molecule is symmetrical, then it will nullify the charge separation. Okay, and we'll see some examples of that also. And then the last one is determine the polarity of a molecule, and this will be yes if the molecule is asymmetric. Okay, so if it is a symmetric molecule, then it will nullify the charge, but for a polar molecule, the molecule is going to be asymmetric, okay, which means there is an uneven distribution of charge. So let's look at some examples. The examples that we're going to look will have more than 2 atoms in it. Diatomic molecules are kind of easy to figure out, because if you have something like hydrogen as an HH, they're both the same. And if they're both the same, then you will not see any charge distribution. And we just did HCl in the previous slide where there was a charge distribution. And because of the charge separation distribution, there is polarity in the molecule. So now we're getting 2 molecules that have more than 2 atoms, okay, in it. So let's take water, okay, and water has oxygen in the middle and the 2 hydrogens over here. The shape of water is bent, okay, as we just learned, and that is because you have oxygen with 2 lone pair of electrons over here. The electron geometry was tetrahedral, but the shape was bent. Oxygen is the more electronegative element, which means that it pulls electrons towards itself, so which means oxygen is the delta negative. But because this is a bent shape over here, these pull that you feel, okay, or the pull that oxygen has from hydrogen is at an angle. This is kind of what this sentence is here about, okay? They're additive because they're vectors, okay? Because something can be at an angle. And so because it is at an angle, you will have some sort of a dipole moment, okay? Which means that water is polar molecule. So let's look at another example, okay, to compare. This line here shows the dipole moment. Okay, again, you have an arrow with the cross here, and this arrow should point towards the negative charge, okay, as we said before. So which means this is where the polarity is, or the dipole moment is. The next molecule to look over is for carbon dioxide, and here we have carbon in the middle and the 2 oxygens on either side, 2 electron groups, which means that we have a linear shape. Carbon has no electrons left over, so this is it. Okay, it's a linear shape. Oxygen is more electronegative than carbon is, so oxygen is pulling electrons on either side. But because this is a symmetrical molecule, and you have oxygen on completely either side, 180-degree angle. Therefore, each of these oxygens are nullifying each other as far as the pull is, okay? The way I look at polarity sometimes is like a tug of war. Okay, and so if one molecule is stronger than the other, it will pull electrons towards itself. But here the tug of war is pretty much equal. Okay, and therefore this molecule will have a zero dipole moment, which means that it is nonpolar. In case of water, the tug of war was being won by oxygen because of the angle. Okay, if water was a linear molecule, then it would also have a zero dipole moment. But because water is bent, it has a dipole moment. Okay, more than zero. All right, let's look at another molecule, and this molecule actually exists in three different shapes. So, or in three different isomers, and don't worry about the fact that they're isomers, they're just connected differently. So let's look at them one by one, okay, and then we'll see what they actually represent. So here is one type of arrangement where you have carbon and carbon attached with a double bond, and then you have the two Cls, okay, going on around here. So the two Cls are on each of the carbons. So this is pretty symmetrical molecule, okay, if you look at it like this. However, this molecule has a little bit of charge distribution because chlorine is more electronegative. It's pulling electrons towards itself, okay. The hydrogen here is not electronegative, which means it's actually ended up to give electrons. So which means here are your negative centers and here are your positive centers. Okay, so which means that there is a net pull. Okay, and the net dipole is then towards the chlorine. All right, and so this molecule is going to be polar. It has a dipole moment. All right. Let's look at another structure. So in this case now the chlorine is on opposite sides, okay, and the hydrogens here are on opposite sides. So in this case again, let's draw the arrows out, okay, and the arrows now we have chlorine going in opposite direction here, chlorine going in opposite direction here, and hydrogens giving electrons. So you can probably predict what's going to happen here. Yes, I'm waiting. Yes, no dipole moment because the chlorine are going to be on either side. And so if it is on completely opposite side, this is a very symmetrical molecule and therefore it is nonpolar. Okay. The first molecule was also symmetrical. Okay. However, the chlorines were on the same side and therefore they were pulling electrons towards that one side. Okay. Here, chlorine are on opposite sides. Let's look at the third isomer. Now this one is easy to figure out because by now you kind of understood the fact that here I have two chlorines on this side. So these are, both of them are going to be pulling electrons towards themselves and therefore the dipole moment should go towards chlorine. That's where the arrow goes. And yes, it is polar. It has a dipole moment. Okay, don't worry about the boiling points over here. Just look at the dipole moment. Okay, the fact that it actually does have a dipole moment, which means that it is a polar molecule. Let's look at some examples over here, okay, of molecules and predict whether something is going to have a dipole moment or not. So GeF4, SF2, sulfur difluoride, and then arsenic trifluoride. Okay, some of the structures we have drawn before, so they're not that hard. So first of all, what we're going to do is, of course, for GeF4, we will go ahead and draw the Lewis structure out. Okay, and so this is the process of drawing the Lewis structure up on the top. Count the total number of electrons, put germanium in the middle, and then fluorine all around. Now, germanium tetrafluoride has 4 electron groups with no electrons left on germanium, which means that this is a tetrahedral electron geometry as well as molecular geometry. Okay, and so if this is tetrahedral, it means I'm thinking of a pyramid. Okay, all the fluorines here are equal in electronegativity, which means that if all the fluorines are pulling electrons towards themselves, it's going to be a very symmetric pull, and that symmetric pull leads to non-polarity of the molecule. Let's go on to the next one. SF2, again draw the Lewis structure of it properly. S is going to be, sulfur is going to be our central atom here, and fluorine is going to be on either side of it. Okay, so now sulfur is here, fluorine is here. Sulfur has 6 valence electrons. 2 of them are bonded and 4 of them are not bonded. 1, 2, 3, 4. 4 electron groups. 4 electron groups meaning that we have, yes, tetrahedral electron geometry, but only 2 of them are bonding, 2 of them are not. So which means we have AX2E2, which means if we have AX2E2, the shape should be actually a bent shape. Okay, and because it is a bent shape, the molecule is going to be polar, just like we saw for water. Okay, in the previous slide, that's what it would be like. All right, so that's your process for determining the polarity of any molecule. So let's look at ASF3, arsenic trifluoride. Draw the Lewis structure. Once you have the Lewis structure drawn out, then you have count the electron groups. You figure out the molecular geometry, which is trigonal bipyramidal for this, because excuse me, 1, 2, 3, 4. It should be tetrahedral, and if once it's tetrahedral and it has only one electron pair that is non-bonding, it means that the shape is going to be trigonal pyramidal. If it's a trigonal pyramidal, I'm again thinking of a pyramid, but then on the top I don't really have any atom. Okay, I don't have any atom over here. Fluorines are all pointing down. If they're all pointing down, it means they're all pulling electrons towards themselves. If they are, then yes, this molecule is polar. Why is fluorine pulling electrons? Because it is more electronegative. Okay, these 3 examples here show you the different shapes, but with fluorine. Okay, so in first case where we have a tetrahedral shape where it's very symmetrical molecule and we have fluorine, even though fluorine is very electronegative, germanium tetrafluoride is nonpolar. Okay, because it's a very symmetrical structure. In the last 2 cases here, where the shape was bent and the shape is trigonal pyramidal, now you have kind of an asymmetric going on. Okay, asymmetric pull going on, and therefore these 2 molecules will be polar. And that's how you determine, okay, if a molecule is polar or not. First, Lewis structure. Second, shape. Third, look for symmetry, and then decide, okay, whether something is polar or not. That's about this for this chapter. Okay, it seems very small, but it is pretty large as far as determining the shape is concerned. It is built upon everything. It's built upon the Lewis structure, and it is built upon polarity of bonds, which we did in the previous chapter. So in this one, you have to understand the concepts of the molecular geometry and VSEPR. You should be able to write the Axe formulas for me. Understand bond angles. You should be able to give me those, electronegativity, and then of course you should be able to figure out if a molecule is polar or not and say whether it has dipole moment or not. Not the numerical value, but at least whether it has dipole moment or not.